So far, the only thing we've done in this unit is which concept? The concept of work, and that's it. Today, we tie it into an even grander concept, which is the concept of energy. And like I mentioned on the first day when we had most of the people out in the literacy prep, it says 3 chapters, but we are not covering all of the contents of everyone. This one we're barely touching on. Those 2 are the main ones in this unit. Okay. So if you have a lot of energy, what can you do? A lot of work. Literally, that's the exact definition of what? Of energy. The energy is the capacity to get work done. Low energy means low work is possible to be done. High energy means high work could be done. Okay? So energy is the capacity to do work. Energy is the capacity to do work. All right. How many people covered energy before? Not necessarily in physics, but in grade 10 science. And obviously, how many people took or are taking chemistry now? Chemistry. Or how many people will take chemistry? Everyone is either taken, or will take chemistry. Chemistry definitely deals with a lot of what? A lot of energy. However, physics obviously is the study of what? All types of energy. We don't call them types of energy. We call them what? Forms. And that's why you always talk about energy transformation. When something transforms, what does that mean? It changes what? It changes form. It changes type. Okay? So you might ask me a question. How many forms of energy are there? Well, it's like asking me how many forces are there. So far, how many forces have we dealt with? Only 5. But are there only 5? No, because the more complex the situation becomes, what do? You get what? You get more types of forces. Same with what? Same with energy. So the first thing we're going to do is a worksheet I actually enjoy doing a lot with students, which is let's see what forms of energy are there and what each one stands for. So I have a little good old matching exercise. Okay, so you have forms here or terms, and then you have brief definition. I want you to do it as a group. Okay, so let's see how many you get right. Oh, by the way, okay, question, Nadim, how many can you count on this column right here? 10. How many can you count here? More than what? More than 10. What does that tell you? What does, by the way, all of them are matchable. So what does it tell you if you only have 10 here, but 13 here? Some of them have what? Multiple definitions or multiple ways to look at it. Okay, so go ahead. Okay, this is the way we're going to do it. Instead of matching this way, we're going to match backwards. So, first question. Internal motion slash or vibration of particles within matter. What did people pick? Raise your hand. Sarah, what did you get? Or what did you say? Say again? Sound energy. How many others did sound energy? Okay, so Haley and Hasib. All right. Any other choices by people? Come on, come on. Pretty sure not everyone picked sound energy. There's a word there that's very telling, very revealing. Yes, Amar. You said what? You said chemical energy. Okay. Any other choices? That's not what the revealing word should make you or persuade you to actually pick. Come on. Yes, Payam. Payam, sorry. What? Which one? Oh, the very first one. What did you pick for internal motion slash vibration of particles within matter? Okay, want to give it a shot? What do you think? There's, by the way, there's a keyword there in the definition, that should make one of those stand out. I'm not saying it's correct, but I'm just saying, wait a minute, we talked about this word. Say it. Kinetic energy. How many people picked kinetic energy? Why? Because of which word? Motion. Anything motion usually has the Greek word or the Latin word kinetic. Any other choices? Haley, you want to say something or no? Any other choices? Did anyone pick anything else? Louisa, what did you pick? So who said sound as well? Someone else? Yes, you said sound. Any? Okay, make a choice. Oh, this is the first class ever where no one picked the correct one. Thermal. Here's the thing. Yeah, backtrack and say thanks. I got it. Okay, everyone. Internal motion vibration. Now, obviously, motion. Listen up. Motion also means what? Motion means what? Kinetic, right? However, whenever we are talking about internal motion and which word? Vibration of what? Of particles within what? That's the actual definition of what? Of thermal energy. Think about it. If you heat something up, what do the particles do more? They what? Like you can actually, like for example, when you boil water for tea, what happens? You can see the little bubbles do what? Vibrate. So that means what? More vibration means more what? More what? Where is it? Thermal energy. By the way, just so you know, everyone, this is the only energy, listen up. This is the only energy you cannot bring down to what? Zero. You cannot purely eliminate thermal energy. I'll tell you why. Does anyone know what's the lowest temperature possible? Raise your hand. You might have covered it in chemistry. It's actually the temperature scale for chemistry. Chemistry people do not usually use Celsius or Fahrenheit. They use something else. Nope, no. For energy, I'm talking about temperature. Temperature. Outside we use Celsius, right? Or Fahrenheit. What's the other name? Anyone knows it? If you're ever doing thermodynamics and chemistry, that's what you always have to use. Not Celsius, not Fahrenheit. Ali. The first one. First one. Come on. Say again. First letter is the no. Okay, but what's the unit? First letter is K. Kelvin. How many people have heard of the Kelvin temperature scale? The Kelvin temperature scale. Okay, eyes up here, everyone. The Kelvin temperature scale is called actually the word that Mo used. How many used? Absolute. Why? Could you get negative Celsius? Yeah, we're gonna get that very soon, right? Could you get negative Fahrenheit? You also could. Could you get negative Kelvin? No. That's why the lowest temperature in the universe is called the what? Hamad, what did you say? It's called the what? Absolute. There's a reason they call it absolute zero, because on the absolute scale, it has a value of what? Zero what? By the way, never say 0 degrees Kelvin. You can say 0 degrees what? You can say 0 degrees. It's not degree Kelvin. It's just what? Yeah, common mistake because we're so used to the word what? Degrees, we say 0. It's just 0 Kelvin. The question is, how, listen up, how low is what? Absolute. Does anyone know how low on the Celsius scale, how freaking super cold is 0 Kelvin? The absolute zero is 273 point. Obviously, it's like a lot of digits depending on the accuracy or the precision. Negative 273.16. This is the coldest. Listen up. This is the coldest you can make anything. But here's the thing. Absolutely no particle could reach that temperature. And let me explain to you why. When you heat something up, what happens to the particles? Vibrate more. So when you cool them down, what happens? They what? They vibrate less. Keep cooling down, what happens? Vibrate less and less. What's the eventual feed? When you hit absolute nothing, what happens to the vibration? Well, here's the thing. You can stop. Quantum particles can't stop. Quantum particles have to what? Have to what? Even by what? Even by a little bit. You cannot make them what? If a particle stops, what's this? So what did you just turn matter into? Pure light. That's it. Particles can't stop. It's, by the way, ask any chemistry or physicist. Can particles ever achieve zero vibration? No. If a particle is brought to zero vibration, you don't have a particle anymore. You have what? You have a packet of energy. What's the only particle that has no mass? The what? Do you see what I mean? That's why you can never reach what? You can never reach what? 0 what? You can reach 0 Fahrenheit. You can reach 0 what? Celsius, but you can never reach 0 what? What's the lowest they were able to reach so far? The very first Nobel Prize given to what they call ultra cold temperature physics. By the way, if you ever see, it's not a freaking freezer. No, there's a field of physics called condensed matter physics. Extreme pressure, low what? Low temperature. They won the Nobel Prize in 2004. You know what they got? What's the small n? They got so cold to 1 nanokelvin. So imagine 0 Kelvin, and you only went 1 nanokelvin up. Perfectly. You know what? The energy vibration of the electrons, they cooled down, was so small. That's why it took until when? 2004 to Nobel Prize. Until they got what? Sensitive devices to measure the what? The little what? The little energy given by those electrons. Do you see what I mean? So small vibrations, they barely could see the what? The energy given out by them. That's why you can never bring it to what? 0. Because if you bring it to 0, you don't have particles anymore. You have pure what? You have pure photon. There you go. Mass is 0. Done. Yes. Oh, okay. Do you know how they actually cooled it down? Seriously. They got a bunch of electrons in an electromagnetic field, hovering in space, nothing touching it. They would shine a laser. It would reflect. That's what we're going to do with electricity and magnetism and laser physics. They would shine a laser. It would reflect, stealing some of the energy, which means the particles would go into a higher or a lower energy state. Lower. Shine another laser. What do you do? Lower. Shine another laser. Lower, 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 until they knew any more laser would just turn it into a what? And they won the Nobel Prize. So if you ever think that liquid nitrogen is cold, negative. Does anyone know the liquefaction temperature of liquid nitrogen? It's about -70 Celsius. Way! Still 203 degrees off. Okay? So that's why you call it absolute 0. No, you can't touch it. First of all, your hand is gone. It's in pure vacuum. It's in pure vacuum. It's the temperature is so freaking cold, you can't even put your hand in the electromagnetic field. It's so strong to keep those what? Have you ever had an MRI? How many people have had an MRI before? Imagine an MRI suitable enough to capture particles in vacuum, not just in your brain. It's insane. Okay. Anyway. Okay. Yes, Nadeem. When they lowered it one more, they couldn't see the electrons anymore. So they knew they what? They turned it into a photon. So they only get. No. They were just testing what? How? No, absolutely not. Energy and matter are conserved. Do you see what I mean? Everything was still there, just turned into light and some heat. Okay. All right. Second one. Motion of electromagnetic energy in. Who can read that word? Transverse waves. It's the word in math. We're going to cover it, by the way, when we talk about waves. What did people pick for this? You picked what? Sound. Why did you pick sound? Is it because of the word waves? Yes. How many people picked sound? Okay. Anyone picked anything else? Anyone picked anything else? It's actually not sound. What's faster than sound? Light. Do we have light here? What do you think light is out of those ones? Radiation. Yes. That's why they call it what? Electromagnetic what? Radiation. Go ahead. Motion of electromagnetic waves is called what? Radiation or radiant energy. So who can tell me what the third one is? That is what? Sound needs what? Sound needs what? Matter. What are the states of matter? Solid, liquid. Can sound ever travel in vacuum? That's why whenever you go to a sci-fi movie and an explosion happens in space and you hear something on the screen, go and ask for your money back. Because it doesn't make sense. Sound cannot travel in space. If we air seal this room right now, like seal every little crack in it, and pump all the air out and I talk, are you going to be able to hear me? No. Why? How can you hear me, by the way? I talk. What do I vibrate near my mouth? Air. What does air do? Keeps vibrating until it gets to what? Your ear, and makes your what? Eardrum vibrate in a way that your auditory nerve does what? Does what with it? Basically, makes it back to what? To actual frequencies and pitches and volumes that your brain understands. So can you ever have sound in space? Which means sound always needs what? In any form, even gas. It goes in gas, it goes in liquid, it goes in solid. Done. So that's sound energy. No. Say it. Oh, astronauts use electromagnetic waves to actually talk. How? That's why in the helmet they talk, and it's like a walkie-talkie. A walkie-talkie transmits what? Electromagnetic wave. Can you, by the way, do electromagnetic waves have the ability to go through space? What's between us and the sun? What's another word for space? Vacuum or nothing. Yet, are we seeing the light from the sun? Boom. That's a proof that light could go through what? Vacuum. Do we feel the heat from the sun? That's another proof that heat could also go through what? Do you hear all of the explosions in space? Say it? Exactly. That means what? The only thing that could travel in space is which kind of waves? Electromagnetic. How about sound waves? They need what? Matter. Okay, so that's sound wave. By the way, sound waves have three names. If they're in air, they call them what? Sound. If they're in what? Solid or the ground, they have different names. Like geophysicists say shock waves, matter waves, or ground waves. And the third one is what? Liquid waves, like tsunamis and so on. Okay. What's this one? That is what? Legit kinetic. Go ahead, everyone. That's kinetic energy. That is kinetic energy. Okay. Energy form that's visible or invisible to us. I mean, we are the most special. No one talks about bats or cats or dogs. We are. What's up? Yeah. There's either visible light or invisible what? By the way, listen up. Who remembers the acronym in grade 10 science for the colors of the rainbow? Because that's the only range of electromagnetic spectrum that your eye can be fired up or excited enough to see. Anyone remembers the acronym? 7 letters, like a name of a person. Roy, G, red, orange, yellow, blue in the middle, and then, sorry, green in the middle, blue, indigo, and violet. Can you see anything past red? Can you see anything past violet? What do you call anything past red? They use it in night goggles, night vision. Infrared. What do you call something above violet? Ultraviolet. Do you see those things? Could you feel them? Do you see what I mean? You know they exist because we see their effect. By the way, just so you know, listen up. You don't have to type this up. Visible light is right in the middle. Okay. What's more harmful than visible light? What's the highest color of light that we can see? Roy G. Biv. So it's what? Violet. What's after violet? Can someone guess listen up, guys. Can someone guess what's more harmful than ultraviolet? The dentists use it. X-ray. And what's the worst, most destructive, lethal? Electromagnetic wave. But what is it called? Hint, it's what turned them into the Hulk. Gamma rays. By the way, could gamma ray turn into the Hulk? No, it kills you instantly. You're done. You can try. Let us know. Keep us posted. Okay, listen up. This is the harmful range. What's the harmless range? What did we say? What's below red? Guys. What's even less harmful than infrared? I'll give you a hint. You use it to heat up food. Microwaves. Microwaves. And what's the least harmful of them all? You see their towers outside. Towers. You listen to their stations. Radio waves are so weak. How come then they tell you you're not supposed to live near radio stations or power stations that emit a lot of radio waves? Why do they tell you that radio waves are harmful? I just told you, and they are the weakest of the 7 kinds. Lindsay. It's not the quality, it's the what? It's the quantity. They come in huge cables with lots of what? Lots of waves, and they can actually what? Basically what? Change some chemistry in your brain. Okay. So that's, what did we say this one is? Radiant or radiation. Stretching, compressing, twisting. Elastic energy, changing of shape without changing the mass. Changing of shape. I know it's almost Friday, but still. Energy still inside the bonds of molecules. It's like food and you haven't broken it down yet. That is chemical energy. That is chemical energy. By the way, when you break those bonds, what comes out of them? What do you think when you break bonds between carbon atoms? What energy do they release? What do you think? Which energy of those is released when you break a chemical bond? What do you use food for? To generate what? What kind of energy? Keep going. Thermal energy. You release all the heat content of the bond itself. So remember, if I asked you what's the energy still in the bond, what is that? Still in the bond. Chemical. Once you break it, is it chemical anymore? No, you released it into mostly thermal. Okay. How about the energy stored in space between 2 magnets? Could either make them latch together or that is legit magnetic energy. Chemical, because there are chemical molecules. This one is what? Magnetic. Energy that makes objects feel hot. No, that would be an insane amount of heat. It will be what? Thermal. Thermal means temperature. That's hot. Okay? So this is thermal energy. Energy due to elevation. Any guesses? Gravity, gravitational energy. Yes. Energy. Okay. What does the sun give you? Radiation. It gives you heat. It gives you light. By the way, just so you know, the sun emits all of these. All of them. The sun emits gamma rays. We are shielded from them with the electromagnetic field of the earth. It obviously emits X-rays, ultraviolet, the entire VL, visible light spectrum, infrared, microwaves, and radio waves. So the energy from the sun is what? Well, it is thermal, but what does it also encompass? Radiation energy. Energy due to the motion of electrical charges coming out of sockets. That's electrical energy. And finally, energy still stored in the strong force bonds of the nucleus. That is nuclear energy. Radiation, radiant energy. What's up? Elevation is gravitational. Okay. Now, do you think in grade 11 we're going to cover all of these? No. We are only covering 3. So I want you to box the following ones. Sorry. Oh. Okay. Box these 3. Those are the only 3 we do in grade 11. Kinetic, gravitational, they go together. And then the last part of the unit, we will focus primarily on thermal energy or heat. Just so you know, which one do we do in grade 12 as well? We still do those three. We add elastic. Again, don't copy, don't box. This is next course. We add elastic, we add electrical, and if we get time, we add radiant, if we talk about photons in grade 12. Okay, what was the symbol for work? What do you think the symbol for energy is? How many people say lowercase e? How many people say capital E? Okay, why do you think it's right? It's capital E. But why do you think it's not lowercase e? Or in other ways, what do we use lowercase? Guys, what do we use lowercase e for? Especially if you do chemistry. A lot. Anything that has to do with electrons is always what? Lowercase e. So this one has to be what? Uppercase e. What can you tell about E? It's a what? It's a what? Question for you. Listen up. Is there energy contained inside of this tablet? Are there particles vibrating inside of it? So if there are particles vibrating inside of it, what energy did we say that is? Which? No. Particles vibration. It was the first one on the list. That was thermal. Okay. Is there thermal energy inside here? Of course there is. Question. What did I just do? By 90 degrees. Did the energy change? Or do you think it's the same? What does that tell you about energy? Does it depend on direction? Perfect. Good. Energy does not depend on direction. Any guesses for the physical unit? What was the physical unit for work? Work. No, that's the symbol. I'm talking about the unit, the measurement unit. Guess what? It's the same for energy as well. By the way, when you talk about power station, they always talk about how much they produce in what? Megajoules. And what's bigger than a mega? Gigajoules and so on. So when power stations produce energy, they talk about them in joules. That means the unit for energy is also joule. All right, joule. So, question for you here. Listen up. Work has the unit of joules. Energy also has the unit of joules. If two physical quantities have the same unit, what does that tell you at least about them? They must be what? Maybe not equal, but they must be. They must be related. And you got it 100%. There's a famous theory or theorem in physics called the work-energy relation. Work-energy relation. Okay. Work is the change in energy. Work is the change in energy. There we go. Go ahead. Work is the change in energy. What's the symbol for change in all of physics and math? Delta, triangle. So there are two ways you can say it. Work is change in energy, which means what? Yeah, go ahead. Oh, okay. Let me ask you a question. Someone tells you, this object right here had 10 joules in it, 10 joules of energy in it, and then after an hour, it had 50 joules of energy in it. So how much energy did it gain? From 10 to 50? 40. How did it gain it? Just by itself? Or probably someone did what? Did work on it to what? To push it from 10 to 50. That's why the work you do is always how much energy has been what? Has been transferred into the system. That's why. Always think of this. Always think of this. You pushed it. If it gained energy, someone else had to do work on it. Question to everyone. What if EI and EF are the same? Regardless of the numbers. They are the same. What is zero? The subtraction, right? Which means what is zero as well? Does that make sense? If the energy of the object, no, not is zero. stays the same the whole time. Has anyone done any work on it? What if the energy of this gets down? That means what? Did someone give it energy or did it lose it? Which means what? It did work. So when you pulled me, by the way, did you gain energy or you lost? But who gained it? Everything in life, one part of the universe loses, the other part what? And vice versa. If no one loses, then also what? No one gains. That's literally what's happening to this right now. So always think of this. If nothing moves or nothing changes its state, no work was done on it. Done.